And hello YouTube, welcome back to our turbulence modeling heat transfer segment. Okay, sorry. So today we are going to do a little bit of LES modeling. I'm going to do a little bit of LES modeling. And we're going to talk about forced convection flows. Okay, forced convection flows over some flat plate or channel. Okay, so this is where most of the convection is forced by some external external driver. For example, there's a pressure gradient or whatnot. But the literature does not have a lot of LES flows for this kind of setup, because Reynolds average Navier-Stokes usually does a lot better. Okay, but whatever I have, I'll just whatever I found, I'll just present. So for flat plate boundary layer flow, for example, one good model to use is the whale model, the wall adapting local eddy viscosity model. So this I kind of gone through in a few videos prior. So using this model, this is pure LES. Using this model, which basically acts as an advanced kind of Van Dries damping function, that will help you to get a decent resolution near the wall, decent wall behavior. Okay, as compared to the Van Dries one anyway. And they use a constant Prandtl number. So they use a turbulent Prandtl number of 0.89 or 0.9, and it agrees well with forced convection. Okay, this one was actually for mixed convection, but anyhow, it's a good model to use for this. All right. For forced convection, most of the flows I found online, they were supersonic flows, because Reynolds average Navier-Stokes, they may not do as good a simulation in that context. So supersonic flow is a special case of compressible flow, where it's like more than the speed of sound in that medium. So that's what supersonic flow is about. And having a turbulent Prandtl number of 0.89 or 0.9 agrees well with forced convection in supersonic flow. Alright, so that's if you kind of fix it. But you see the Prandtl number changes for different flow setups. So this 0.4 to 0.6 was at a low Mach number, or incompressible flows, or compressible flows that you can treat as incompressible because they're flowing so slowly, below Mach 0.3. So this number kind of fits for that. This one's for coarse grade, but apparently also supersonic flow heat transfer. This for supersonic flow heat transfer, this also works. Okay. So, but if you wanted to do a dynamic Prandtl number, dynamic turbulent Prandtl number, you could do it in a similar way to the dynamic Smagorinsky model. Okay, if you don't want it to be fixed, and then you want it to change and then agree well with your wall regions. Okay, because being close to the wall is where the most critical heat transfer process happens. The most thermal resistance is there. Okay, so again, you have a very similar log law of the wall function. If you have a forced convection flow, it's only for forced convection. So it's a T plus versus Y plus. Okay, so oopsie. So what Prandtl number do you want to use? Do you want to use a constant Prandtl number, or you want to use something more dynamic? So if you want to do it more dynamic, it'll be so-called more accurate, because you could account for the turbulent fluctuation difference in the wall region as compared to your free shear zone. I mean, very far away from the wall, right? So this is how you do it. Okay, this is the formula they use. It's the dynamic Smagorinsky coefficient. Then you multiply into some filter length scale. Then you have these two quantities over here, which I will skip the derivation. I will just tell you what they are. Okay, what this EK and FK is, and then you see these curly brackets here. These curly brackets here represent spatial averaging. Means to say you see these quantities EK and FK, you multiply them together, then you take a spatial average of them in the local vicinity. I will skip the details on that, but that's how they do it. So EK is 1 over rho. This is the doubly filtered viscosity. Remember, we need to have two filters, a test filter and your normal filter. So the normal filter is the bar, the test filter is the hat over here. If you're not sure what a test filter is, please go and study the dynamic Smagorinsky model. Look at my videos, a few YouTube videos back in my turbulence modeling playlist. Again, it will be in the description, so yeah, look at it if you're not familiar. And yeah, you will have this a singly filtered rho, then you have this U tilde. Now this U tilde is a slightly different form of the filter. I'll get to that in a bit. Okay, a slightly different way to filter, especially for compressible flow. So okay, you multiply these two filtered quantities together, then you filter them again, and then you have rho times T, okay, singly filtered each, and then you filter them again, and then you subtract from the rho hat, the filtered filtered what do you call that? Filtered filtered density. Then you have your velocity here and your temperature. Both are singly filtered. Why there's a twiggly line, the tilde here, I'll explain shortly. Then you multiply them together and then you filter with the test filter. FK is over here, doubly filtered the filter length scale, delta. Then you have doubly filtered density and doubly filtered strain rate. And then here you have a doubly filtered temperature. Okay, so this is a temperature gradient, doubly filtered temperature gradient. You subtract off, okay, the singly filtered length scale for your filter length scale, singly filtered, which is your normal resolve density. Then you have a singly filtered strain rate using the test filter. Then you have singly filtered temperature gradient. So this is again the tilde, which is a bit different. Okay, remember we do double filtering here, and the density here can change because it's a compressible flow. Remember, supersonic flows are only applicable to compressible flow. Okay, so the above applies to compressible equations. Of course, if your density is constant, you can just say this is constant, and you can just factorize them out, take them out. That will be okay. And if this is constant and this is constant, you can also factorize them out, because the filtered constant velocity is the same as your normal time dependent constant velocity, which is just constant. Okay, if the rho is constant, you can take it out the filtering integral. Okay, so if you're not sure what the filtering integral looks like, please go and visit the Smagorinsky model videos, the early videos I have on LES. Okay, the tilde line here means Favre's filtering. It's a name, it's a way to filter for compressible quantities. Again, I'm not sure if I pronounced his name right, but this is what you do. Okay, so we haven't introduced this before because we were dealing mostly with incompressible flow. So let's say you want to filter this velocity, right? You have to filter this velocity, or you want to filter this mass velocity, right? So if you want to filter this velocity, I mean, you still have to, because of your continuity equation, you won't use your absolute velocity as your way to introduce mass in or out. they will use this mass velocity, which is this product of rho and u, which will give you the mass flow rate per unit area. Is a mass flow rate per unit area. Alright, so if you want to do a Favre filtering on u, all you have to do is that, okay, you realize that rho u, and you filter this product, that will be equals to the filtered density, the resolved density, and then this u tilde. So u tilde is defined like this. You divide this filtered mass velocity, which is rho times u. You divide this filtered rho times u over rho, and that's how you get the Favre filtering. So this is all Favre filtering is. So, but you don't want to keep writing this notation down. So we use this tilde to represent that. So if you see this t tilde is actually rho times t. Then you do this filtering once over it, and you divide it by rho. That's a Favre filtering. And again, brackets mean spatial averaging. So we have LES simulation of such flows. From the dynamic procedure, how they calculate this dynamic turbulent Prandtl number and how it varies from the wall. Prandtl number is 1 near the wall and 0.5 near the center line. So yeah, this one was from Wang and Fletcher. I'm not sure if it is this supersonic or what, but okay, so anyway, these values, okay, I just checked, I think. Yeah, I just kind of double checked. These values were low Mach numbers. For low Mach numbers, Mach 0.01. This is effectively incompressible because a Mach number of less than 0.3, I think this is 30 times less than 0.3, can roughly think of it as incompressible flow. So it's easy in that sense. Alright, so from this dynamic procedure to model this kind of flow, you notice that the turbulent Prandtl number goes to 1 near the wall for this LES, and it goes to 0.5 near the center line. Okay, so if you have a channel flow, like so. Alright, so this is y equals 0. This is minus y equals to minus h over 2, where h is the whole length here, the whole length of the channel, and then you have the h over 2. Okay, so this is y, and you have a Prandtl number profile, turbulent Prandtl number profile. Then you would have it near the walls, and then you kind of dip very fast, and then close to this wall it rises up again somewhere here. So this is what the profile looks like if you calculate it out dynamically for this non-supersonic flow. So near the center line is about 0.5. Okay, so again, conduction sublayer, which is near the wall, the Prandtl number is 0.9. Log law region, you can use, I think, 0.5. That should be fine. So the Prandtl number actually varies from point to point. So I mean, if your CFD solver has a wall function, you could use the Prandtl number 0.9 there if it's open form. If open form allows you to do that, define one Prandtl number near the wall and then one for the rest of the flow. If that works, that works, and this is shown to be okay. And you can compare this to Prandtl number equals 0.85 mostly, or 0.75 if you have a slightly kind of a different Prandtl number fluid, a high Prandtl number fluid, so this will drop or something. Yeah, I have to recall how the Prandtl number changes with turbulent Prandtl number, but never mind. Yes, you can just have a good comparison between this Reynolds average Navier-Stokes Prandtl number to this LES Prandtl number. You'll see that again, this turbulent Prandtl number can vary quite differently, and the value it takes for most of the flow is about 0.5, which is lower than your Reynolds number. So this is not actually compared to experimental data. because again, like I was elaborating in the last time, it's very difficult to measure quantities of turbulence flux. Okay, so the setup, if you're interested, okay, the setup for this was, if you want to know how fine the grid is, it's a 65 by 65 grid over 2 pi delta. Delta is this channel height divided by 2. Okay, so 2 delta is the channel height, which is h. So it's pi times h times h times pi times h. Okay, channel dimension. Okay, so this is okay, h is the channel height. You have this part split into 65 grids, 65 spaces, and this part into 65 spaces as well. So this is how fine your grid is. So yeah, okay, if h is the channel height. Okay, so this is roughly how fine your, it gives you an estimate of how fine your LAS simulation ought to be. Okay, it's about this kind of distance. All right, drawbacks. So these are some drawbacks of LAS simulation in large channel flows. Okay, it tends to underpredict skin friction and Nusselt number. Okay, so skin friction can go as low as 12.5% compared to, let's say, DNS data, and this is for low Mach numbers or incompressible flow. And this data was actually taken from this same paper, Wang and Pletcher. So let's just do Wang and Pletcher. So this is the paper. I forgot to insert the citation in. Right, it's lagging now. Hold on. I will try and fast forward. Okay, never mind. What is it? Okay, this is weird. Oh, okay, here we go. Wang and Pletcher. So for low Mach numbers, it will underpredict this skin friction. Okay, and most of the error, okay, drawback of LAS in heat transfer or convection. Okay, maybe I won't say drawback, I'll say error. Okay, so there's this underprediction of low Mach number regimes. Most of this comes from difficulty in LAS. So LAS usually has difficulty predicting properties near the wall, but in terms of temperature profiles, these are pretty well matched, except for some cases we get from, I think, this paper, 10% under prediction of near wall velocity as compared to DNS data. Anyway, it goes to show overall LAS has some difficulty near the wall. Unless you make your grid size so small it almost becomes a DNS, then you can kind of trust it. Alright, so there's a general lack of turbulent channel for LAS data online for incompressible flows, because this is actually quite trivial. You can either do it yourself and you compare to some flows online, or you use the Reynolds average Navier-Stokes. It's still better to use the Reynolds average Navier-Stokes in this case, right? And that will often give you better results because yeah, it's empirically modeled, this wall functions. So LAS doesn't resolve all the turbulence there, so we have some difficulties there, especially near the wall. Near the wall, in this law layer region, near the wall, the turbulence here, the turbulence here is a small turbulence. The majority of the turbulence here is small turbulence. And majority of the small turbulence will fall into this region, which LAS near the wall, there is not a lot of this low frequency turbulence or large turbulence. You have most of it in the small regime, and most of it will have to be modeled with LAS. And LAS modeling of this small little turbulence near the wall, it may not be accurate because LAS by and large you assume that the turbulence is isotropic and etc. May not be true near the wall, and near the wall the turbulence may be structured in a certain fashion. So it's not as good for modeling near the wall. Again, there was some success with Yeoh and dynamic Smagorinsky for supersonic flow near the wall, and the temperature profile is near the wall is within 2% of DNS data. So that's very good for Yeoh and dynamic Smagorinsky. But in this paper, it shows that the Yeoh model, the wall adapting local additive viscosity model, overestimates by 20% compared to DNS. So for dynamic Smagorinsky, it looks like it usually underestimates the friction near the wall. For Yeoh, it may overestimate for this case. So you can kind of give yourself a plus minus error. It's plus minus 20% compared to DNS of skin friction coefficient and Nusselt number. Okay, so you can go and look at these papers. They are very telling of this. All right, which is okay compared to RAND simulation over predicting Nusselt by 30%, quite an improvement. Okay, so it's still better. I mean, the error bars are smaller, so to speak, for LES models in general. But I mean, there are still difficulties in this near wall region. So we kind of have to switch things around a bit. Maybe LES near the wall may not be as good. Okay, but this is for forced convection. This is for forced convection. For natural convection, the story is slightly different and it's sort of interesting. So I will talk about this in the next video. Thanks for watching.